Hi everyone and welcome back again to my channel. Today we're going to complete the tutorial we started last week in basic electronics components. We're looking at um, transistors, MOSFETs, and we're supposed to continue on flip-flops and comparators, but the video got truncated after 21 minutes, so let's see if we can catch up. That will be our video today and for the weekend, and next week we're going to go into building um, actual projects. All right, so stay tuned as we continue this video tutorial. All right, so let's look at the let's do a little bit of review what we did last week. So last week we looked at MOSFETs. So we did the N-type MOSFET and the P-type MOSFET. So this is the P, there's the N. Alright, so when the arrow is coming out, we know it's the P. When the arrow is going in, we know it's the N. So you can look at it. You can watch the video from last week. So today we're gonna look at other things. So let's look at quickly. We'll try to make this video brief. So let's look at comparators, okay? And then we're gonna look at flip-flops as well. So for a comparator, if you look at an op amp, it has two inputs, the non-inverting and the inverting. Then this is the output. Let's say this is a power supply. So when let's look at this, use this table to guide. So this is input and this is output. And we'll say when the positive inputs, that will be let's use different colors. So this is A and this is B. So and then we'll say when A is greater than B, so if A is greater than or equal to B, the output is 1. Else, when A is less than B, the output is 0. So we can probably in a subsequent tutorial we're gonna build a circuit. So when you I'll just pause a little bit here and explain a little bit more. When A, so this is our output. Let's use a different color for the output. Let's say orange. So this is C. All right. So that's the comparator right there. So we can use this to design. I'll give you a circuit idea: light chaser, or light follower, or line follower actually. So if you have, let's say, let's draw another comparator. So let's say we have a resistor here. We have the same value here. If this is going to the positive and this piece is going to the ground, if this value is R and that value is R, then the value here is V over 2. Okay, this resistor looks neat up So let's have the resistor. This looks a little bit better. So let's do the same for the inverting input. Let's put another resistor there. And in this case, let's use a different color. Let's use a different color of resistor. Let's use light blue. So let's call this R1 and R1. If this is equal, then at this point, the inverting input, the value is V/2 as well. Okay. We know this from voltage divider rule, right? Same current flows through them because they're in series, the resistors are in series, and then voltage V is equal to IR. So voltage dropped across each resistor is the same, then because the current flowing through is the same. So if the voltage then, if V is equal to, let's just use a number, let's say 4, then V at, we call the inverting input B and the non-inverting input A. So if voltage at A is equal to 2. At the same time, voltage at B is equal to 2. Therefore, voltage at C is equal to 0. No, it's not 0 because they are equal. Remember the table? When they are equal, it's 1. So we fix that. This is 1. Now we can design something. Maybe we can build something next week on this, or maybe subsequently. But here, let's use a different color here. Let's say here we have an LED. Let's say. The LED will glow under this condition. Now, if we change the value of R1, if we change the value of either of these R's, so let's say if we change this value, let's use this. We change this value or this value such that V at A is less than V at B, then the LED will go off. Right. So how can we do this? How can we do this? So I'll give you an example. Remember we talked about resistors as different types of resistors. We talked about light dependent resistors. So here, if you use a light dependent resistor for R or R1, then the value will change depending on the amount of light falling up on it. So I'll give you a circuit idea, and I want you to build this. I think at this stage we'll be taking some bold steps and building stuff. So let's redraw the circuit and take some bold steps. If you put comments, if you need help in the comments, I can build it out. Otherwise, I will assume that you understand it. So we're just gonna use a regular resistor here, but here then we're gonna use a different type of resistor. Light dependent resistor. We can do the same twice. Just use regular resistor here, and then here we're going to use again light dependent resistor. All right. You can use a resistor here to limit the current flow through your LED. Okay. So with these values, you can use equal values here actually, and then this will be R L L L D R. Yeah, we'll just use the same value. Let's say R1 prime and then R1 prime. They're the same. Use the same value for both. Then, depending on the light falling on them, the value, the voltage at A. Remember, this is our point A. This is our point B. This is our point C. The voltage at point A and point B will depend on the value of the LDR. As long as you get the same values here, you're able to, and then you make sure that light falling on them, if they are the same, actually you don't have to ensure anything. Just have the two photoresistors will look something like this. Correct. When you expose these two, and then this will of course go into the circuit. When you expose these two to light, the output the condition of the output will depend on the amount of light falling on each. When they are equal, the output will be high. If R and if let's call this, why don't we just give it a number? Say R1 and R2. Let's change this back. Let's change this a little bit and just put, okay. Let's call this R3 and this R4. Forget about the prime. So, and then in that case, we'll say that R1 is equal to R2 and R3 is equal to R4. Okay, so we can reference each one separately. All right. So when you have this system here, so this would be, let's just call this R5, and then LED 1. Okay, I think we've labeled everything. And of course, this is your positive supply, and that's ground. So when R1 and R2 are equal, and R3 and R4 are equal, the output will be high. But when R1 and R2 or R1 and R3 are not the same, if the value of R1 and R3 are not the same, and the value of value of R2 and R4 are not the same, the output will depend on which one is higher. Example, let's say R1 is 2 times R3. Let's say R1, if R1 is 2 R3, it means the value, this means that the V at A, it's gonna be and let's say at the same time, okay, let's say at the same time, okay, we'll just take it this way. is going to be less than V over 2. We know that because the voltage dropped across R1 will be higher than the voltage dropped across R3, and since you measure with reference to ground, the voltage dropped here will be less than the voltage drop here. So the voltage drop here will be 2/3, and this will be 1/3. Okay. And if at the same time, this is important because you got to look at the second arm of the resistors. If at the same time R4, if at the same time R4 is greater than R2, this will mean that voltage at B is greater than V over 2. And if we use the same token as above, let's say if R4 is 2 times R2, we know for sure that V at B is 2 over 3 VCC. Right. So in that case, the output will be low. So when you expose these two LEDs to different lights, depending on the light falling impinging on the light dependent resistors, the output will be controlled. So try this, build this out, build a circuit, pick a value of resistor R1 and R2, then pick the same value for R3 and R4, and try to shield the light falling on each one and monitor the output. Alright, as the light increases, let's say the light falling on the resistor increases and the value of the resistance changes. If they are not equal, if the change, the value of the change is not the same for R3 and R4, monitor the output. We're going to use this to control LEDs, to control motors, to control light followers. If when you build a circuit, we can build a simple circuit that will follow light on the floor, and we can use this to control the movement of the motor. Right. So we're going to stop here for comparators unless we get questions. So let's look at flip-flops. Flip-flops are very interesting. So we're going to look at maybe 3 or 4 types. There are many types of flip-flops. All right. So one of them we're going to look at quickly is the JK flip-flop. So JK flip-flop, it's much like other flip-flops, but in this case you have almost all flip-flops, I would say, has a Q, which is just your regular output, and a not Q, which is opposite of Q. I think it just makes sense that way. Then you have the J input, you have the K input. So J and K. Then you have the clock. So the clock signal, the clocking signal with the clock, we always have an arrow here. I don't want to miss that. So you have a signal here, and then you have a signal there. When you send the signal clock, it will act upon the J or K. So let's take an example. Let's say we have a value A. It will have a value 1 on J input. So have 1 here, and then let's say we also have 1 over there. Okay, I'm highlighting something I didn't need to. Yeah. If you have 1 on both J and K, right, and we send a clock. When we send a clock, the output will be 1 and 0. And when we clock it again, it will just flip it. Remember, it's flip-flop, 0 and 1. As you clock it, it flips. As you keep clocking, it keeps flipping, right? So this is a toggle action. When you have both input J and K all ones, as you send the clock signal, the output will keep flipping. So this is flip-flop. Now, if you want to set the output, if you want to set Q, so there's a flip-flop action or toggle action. Let's call this toggle. Another way is if you want to do if you want to set Q to 1 all the time. So let's take the set. You know what? I'm going to redraw this a little bit for this. I'm going to use this as input. Let's change this and draw it a little bit different. Let's say this is in and that is out. And let's say this is J and that is K. I didn't give any room for clock. So let's take part of the output for clock. CLK. Alright. Then that stays as our Q and not Q. Q and not Q. Okay, that's better. So we can just fill out this table, right? So let's say we have J as 1 and K as 0. If you have J as 1 and K as 0 and we clock, so we send a clock to the clocking input, what's going to happen? The Q, if I send a clock, Q will be 0 and not Q will be 1. Right. And if I set the clock again, sorry. So when I set this and at the time that my Q, sorry, let me delete this. No, I didn't want to do that. I want to delete just this and this. Yeah. Okay, so what I'm trying to achieve here is to keep my Q as 1 all the time. I will set my Q as 1 all the time. So if I send a clock and say previously, let's say previously, if previously Q was 0 and not Q is 1. So this could be a state, right? Previously Q was 0, not Q is 1. When I send a clock, it will flip my Q to 1 and it stays 1 all the time. It doesn't matter if whatever clock I put, it stays that way, right? So J is 1 and K is 0 and I send a clock, it will set my Q to 1 all the time. Now, what if a situation where I have both of them as 0? I have Q as 0. I have J as 0 and I have Q as J as 0, K as 0, J 0, K 0, and it doesn't matter my clock. It doesn't matter. It's a don't care. When I clock it, it will my Q will be 1 and not Q will be 0. So no change. Q will be 1. When I send clock, not Q is 0. That'll be no change. All right. And let's build a different one. Let's look at a different one. This will make more sense once we start building something, but let's look at a different one. Let's look at the D-type flip-flop. Okay, so we looked at JK, let's look at D-type. If you have any question, we can go back and look at it again. But most of them, in fact all of them, will have Q and not Q output. So for D type, you just have your data input here, your D input here. So this is just simpler than the JK, right? It's a simpler version. So once you send data, it will flip. So whatever Q and not Q, sorry. So if let's draw this a little bit better. So this is D, this is Q, this is not Q. Not Q means it is not Q. So in this word 1, the word of ones and zeros, if it is not 1, then it's 0. If it's not 0, then it is 1. That's what it means. So if I send my data here, and let's say we start with Q as 0 and not Q as 1, when I clock it again, it will just change. When I clock it again, it will just change. So it's just like regular set reset. So let's look at set. So this is D type. Let's look at set reset. So just like the name implies, you will set it and you will reset it. Again, Q and not Q. Set and reset. Okay, so in this case, if I send a clock input, if I send a signal on my set, so let's draw the table. So these are all I think positive going, set, reset, Q, not Q, or Q bar. I think I need to rewrite this so that my Q, not Q, will have its bar. Yep. So if I have 1 and 0 here, and I have 1 and 0 here, when I do 0, 1 here, then this will reset to 0 and 1, and so on and so forth. So you send a signal to clock, and then you send a signal to reset it. And sometimes you might have a situation where your reset, let's say your reset is 0. Then in that case, if you don't want to reset it, let's use this case. If the set is negative going, so you have to go lower to reset it, sorry. If that's the case, then you have to make sure that when you're not resetting, you have to use 1. So for this table, it will look something like, to reset, it has to be low going. So maybe set, reset, has to put bar there, then Q and not Q. So in this case, if I want to set, I have to have 1 1 to set it. Let's say I get this, and then to reset, this has to be 0 to reset because it's negative going. So I have to use 0 to reset it to 1 0, and this, of course, I can make it 0. But it will really be a don't care, so I can even use an X there because this will be a don't care. X will represent a don't care, doesn't matter the state, because once you reset it, it's going to reset to what it was originally. So X means doesn't matter. X could be 1, could be 0, doesn't matter. So once you reset it, it will change the values. But then if the value comes back again, if you set it again, but the reset stays 0, it will always reset. So if you want to set, you have to make sure that the state of your reset is the opposite. Negative going will reset in we can check on the internet and see what value of flip-flop you're using, what type of flip-flop you're using. If the reset has a bar on it, then it's going to be reset by negative going signal. So we're going to look at what other one, and let's say toggle. Toggle is similar, so just toggle is similar to D. So we're not gonna draw that again, so we can just call this toggle. And then for set reset, many people, you can also convert this to look like you can convert your set reset to look like a D, or yeah. So in this case, you can, if you have this Q, you know what? I've been drawing this wrong because you put the labels inside, and then set reset. So you can do this. All right. So then, or you can use not Q to reset. Like when you send a signal in here, it will serve as a clock. When you send a signal in, oh, you know what? I think let's draw a table for this. Okay, let's draw a table. Let's say this is 0, this is 1. 1 will set. So when you send a clock reset, will be low. If you set low, Q will be 0, not Q will be 1, then it will reset. You can also do this with JK. So if this is J and K, you can connect the input to the output. You can also do this with any other type of flip-flop. So the states will change all the time. When you clock it, it will change. When this changes back to 0, I think I probably drew this wrong. So let me try to fix that. If this is Q and not Q, you probably want to do this to reset, and then set is over here. That is your output. Yeah, so when this is, if this is low, that means anytime you get a 0 here, you reset. So the first time you're gonna have your table, it will look something like this will be my set, this is my Q, this will be my not Q. If I do 1 here, this is gonna be 1, and this will be 0. And because it is 0, it will reset the signal back to what it used to be. All right, so do I want to use this? If I'm using, let's say I'm using an active high flip-flop. So this won't reset my system, but then when I clock it again, send another signal, and this should now change to 0, and this will be 1. So it's going to function as a toggle. So when this becomes 1, it will go reset this, and this becomes 0. So this table is going to continue. When I clock it next time, it's going to go 1 and 0. When I clock it again, it's going to go 0 and 1. All right. So confirm your flip-flop if it's active low or active high. And whichever is the case will determine what you're going to use to reset it, if you're going to use Q or not Q. So always look at your schematics diagram. Look at the spec of your components, right? All right, so that will be it. What else did we say we're going to talk about today? We looked at comparators. Yeah. And then we looked at flip-flops. So what we have left in the title. Last week we were looking at some transistors in I think we talked about this at length, but I'm just going to sign off with transistors. So this is the MOSFET we looked at, the N channel, and then we looked at the P channel. All right, So we looked at this last week, and a few other things. So we're going to be using this for our inverter. Subsequently, we just getting ready with that. It's going to be microcontroller inverter, microcontroller based inverter. We've built this before, but we're going to redo it again and show the codes that we used in the microcontroller. Alright, microcontroller. This will be heatsink for inverter, and we're gonna have the MOSFETs attached to it. We're gonna have our transformer. So this will be one of the subsequent videos we're gonna build. So stay tuned. We're gonna draw the full circuit diagram for you then. But stay tuned. This will be MOSFETs. Please help us to share this video, share the link, invite your friends to like and subscribe to our channel. And we're gonna be, so I think this will be it on basic electronics, unless we get some questions and comments. We're gonna be leaving it here, and we'll just go into building more things, and a little bit more microcontrollers, a little bit more node MCUs, Arduinos, and all that. And we have a camera system that we're gonna demonstrate as well. So let's help to broadcast this. Tell your friends to like and subscribe, and I'll see you in the next one. Alright, so that will be it from us today. Thank you for watching. Thank you for always coming back. Please remember to tell your friends about my channel, and you can put your video ideas, circuit ideas down. You know what I'm doing right now, this series we've been doing for the past 2 or 3 weeks now was a response to a question on our channel. Someone had asked us to show how to, or to teach how to read and understand electronic circuits, and we thought this is just our approach. We thought that the best way is to learn the basic fundamentals, and once you learn those, you can build up from there. Some of these circuits I'm drawing right now are things I picked up from a long time ago. We use them to build things like combinational lock and all that. You don't need that right now. You don't need flip-flops for combinational locks anymore. You can do that with ATtiny. And easily you can do that easily with ATtiny. But then we had flip-flops. So flip-flops are memory devices, so whatever state it is, it will remain there unless you send another clock or send another input signal. And this happens to be as long as the battery is there, as long as power supply is there, it will remember its previous state until you tell it to change it. So we use that to build combinational lock, so you can have 4 flip-flops or 5 flip-flops. I remember one time we built remote control door lock, and to be able to send the transmit signal to, or the unlock signal from your phone, from your, not phone this time, but from the remote control device to your door to unlock it, you just send one code, just single code to the door, and it will unlock. But for us to do that, before you can send the code is pre-programmed, of course. Before you send the code, you have to get the combinational lock. Once you get the combinational lock, then you send the code. And we built a fail-safe or a security device there, that when you get the combination wrong, it will reset your flavor. So when you hear me talk about set reset, so you use the reset. Say, when I get this wrong at this stage, go reset everything so I can start over. And you can use a count to say, when I do this 3 times, block it for certain number of times. So in that case, we use 5-5 timers to create a delay. When you get it wrong for so long, you enable a 5-5 timer, which will block you from doing any other thing. The 5-5 timer simply comes on and gives a logic state, and that logic state is used through transistors to reset all your flip-flops. and keep them reset until the time let me just give you the signal. So we use the monostable interval. So this period here is your monostable interval. So we use monostable multivibrator. So we have 555 timer. Pin 2 is connected to I think through a transistor. So we have a transistor to ground, and the signal coming from the flip-flops connects to the base of the transistor, and this one goes to the positive supply. So once you get the condition wrong, this signal shows up and enables this transistor. The transistor pulls down pin 2. Even though it's momentarily, the monostable interval starts, which is this period. So however delay or time I want to include, you make sure that it's covered by this your T. So this is your delay. That means whenever the output, which is pin 3, is high, you use that to block or to stop other flip-flops from to reset all the flip-flops. So whenever you try to set it, it will reset right away. So you do that until this monostable interval is out, and then the person can try again. So we built all this, but there were a lot of hardwired circuit, right? You have, can you imagine, just right here I have 1555 timer here. I have one transistor, and then I have bunch of flip-flops. If you want to have 4 buttons, then you have to have 4 flip-flops. If you want to have more, then you have to have more flip-flops even. So there are a lot of but sometimes you can buy a circuit that has 4 flip-flops inside, 2 inside, or 3 inside, depending on what you buy. But still, you're gonna have a lot of hard wires. But today, you can do all this using an ATtiny, just one system that is the size of 1555 timer, one chip, size of 1555 timer. You can program all the codes inside this. I can have a dot matrix keypad attached to it to give you the same function, right? You have about 6 I/O pins. So okay, the 3 up here and 3 over here. So this is positive, this is 0 volts, and you have your microcontroller. Anyways, so with this you can have when you have 1 2 3 1 2, so you can have how many combinations? 1 2 3 4 5 6 7 8 9. You can have 9 buttons connected, so with just this one chip, and you can have 4 with 2. Let's say you can have 1 2 1 2, so 1 2 3 4. You can have the 4, and you still have 2 I/O pins, 2 extra I/O pins to perform other functions with the one microcontroller. It's so much easier, and you can change the codes from time to time versus the hardwired system where once you finish the soldering, you're done. So this is much more efficient. So we're gonna teach more of this going forward. If we have questions, you can ask us. And so my friend, this video is dedicated to you actually, and if you have more questions, let us know. But I want you to build up from the basics. Just pick up a few things and try to experiment. Anything that we've built here, try to do them. We've done transistors and switches, so you already know how to use this. We've done 5/5 timers. If you want to try this, you can try it. We did an older video on MOSFETs, but we're going to do more, so you don't have to worry about that. We talked about flip-flops when we talked about 5/5 timers, so you have an idea, but we'll just try to add a little bit more. We also talked about op-amps and comparators actually when we talked about 5/5 timers, but this is a little bit more for you, so you can let's see what again. Okay, that's what we talked about today, and this is key for you for a comparator. When your inputs, your non-inverting input is greater than or equal to your inverting input, then always your output is high. And conversely, when the non-inverting input is less than the inverting input, the voltage at that input, then the output is 0. So that will be it from us today. I know this video is a little bit longer than I thought. I thought it was going to be under 20 minutes, but it's a little bit longer. If you learned something, that's great. If you didn't, please keep coming back. There will be something more for you. Probably you know these things that I'm talking about right now, so it's totally okay if this is not new to you. But if it's new to you, then just try to build some of the things we're teaching, we're showing you here. If you know someone who's a student in any institution, they can come here. If they're a student of electronics or electrical or computer engineering, they can come here and ask some questions, and we can help to explain some of the things that the lecturers are teaching. Some of the things, when I was in school, there were some things that the lecturers were teaching that were a little bit harder to understand during the class time, but we had tutorials after class, and we made those things a little bit simpler for other people. So if you're one of those that you need a little bit more help, then you can always count on us. If you come here with your questions, we're going to try as much as possible to provide help and support. All right. I will sign out. See you next time.